Let's see what's the objective of this lecture. You remember we said we are gonna talk about four things and we finished the sets. Now let's see what is the Cartesian product. So we need a motivation why we need to learn the Cartesian product. You remember I said set is an unordered object, a structure, let's say. It's an unordered structure, right? How about what if we need a ordered thing? You remember I introduced the lists as a collection that order matters for them. So we have already lists for the ordered structure or mathematical structure, but the question is, how can we model these lists? Okay, we know what we are looking for, an ordered collection. And we are gonna, respond to this question. How can we mathematically model an ordered collection or lists? Mathematicians introduce a new structure, a new mathematical structure called n-tuple. And we denote that n-tuple with this, with parentheses and all of the elements here. Okay, and I am sure that you have used a special case of this n-tuple, which is order pair or two tuple, in many mathematical courses or even the physics or somewhere else, right? So how can we create this n-tuple? That's why we need Cartesian product. Cartesian product's job is to create these n-tuples. And Cartesian product was named after this great French mathematician, René Descartes. Okay, here is the definition of Cartesian product. We have two sets. You remember I said sets are so important. So now it appears here. We have two sets and we define Cartesian product A cross B by this set builder. What is this set builder about? It is saying that we have some members whose pattern is this. So it is using the pattern template, whose pattern is like this, and in such a way that the first element belongs to the first set and the second element belongs to the second set, right? And let me take some example to clarify that. If set A is 0, 1 and set B is 3, 6, 9, what is the Cartesian product between these two guys, A cross B? So from the definition, we know that we need some ordered pair here, right? And in this order pair, the first element should comes from this set, the second element comes from here. So it will be 0, 3, 0, 6, 0, 9, and then 1, 3, and so forth. The last one will be 1, 9. Okay, so this is the Cartesian product that we will be using in this course a lot. We can extend this idea to n sets to create what? N tuple, like this. Okay, so we have n sets here, and with the same definition and same concept, we can create n tuple by applying this rule. Okay, we have some properties for Cartesian product. This is one of them. If you make a Cartesian product between A and phi, from left or right, doesn't matter, the result is phi. Okay, I ask in an exercise in the future, in the next slide, to prove this. Another property is that the Cartesian product does not have a commutative law. Okay, actually there are more properties, but these two are important for us. So here is some exercises. We have two sets Q, we call it Q0, Q1, and sigma AB. I ask you to create this Cartesian product. So this Cartesian product, so first you would need to make this union Q0, Q1, Cartesian product, sigma union lambda. So sigma is A and B, and when you union it with lambda, we have lambda here. So you need to make a Cartesian product between these two, which is very easy. Another exercise, I ask you to prove this. How can you prove this? Let me give you a hint. You need to make that definition, that set builder definition for this, and after this, and based on whatever I said in the previous lecture, quickly you can prove this. It's so easy. And another thing, I ask you to prove that if A cross B equal to B cross A, then one of these conditions should be satisfied. So between them are or, you see. So either they should be equal or one of them should be phi. Okay, this is whatever I wanted to tell you about the Cartesian product. Let's switch to another one. What we got for the functions. As usual, we need a motivation. Why should we learn the function? Okay. From time to time, we need to have a relationship between two sets. What does it mean? Let me take a very simple example. What do I mean? A relationship between two sets. We have, students sets here and the grades sets here. And let's say this is a, quiz. Okay, and these are the grades of these people, right? For example, John got A, Tom got C, Adam got A, Eve get F, you see? So we have a relationship between two sets now, right? And this relationship needs a new mathematical structure, a new mathematical concept. And guess what? Function is this thing that we are looking for. Now let's define the function. What is function? Let's assume we have two sets. Let's call it D and R. So this D, stands for domain. R stands for range. If there is a relationship between these two sets, and if we can, by a rule, map John to one of these, letters, Tom to one of these letters, and so forth, this is the concept of the function. But here I emphasize that this mapping should be unique. For example, if you are mapping John to a letter, this mapping should be unique. You cannot map John to A and at the same time to B, right? This mapping should be unique. That's why I am emphasizing that. So in that case, we call the first set as the domain, the other sets as the range, and the function is denoted by this relationship. So this is the name of the function. Let's call it G. And this is the domain and this is the range. So the elements of domain will be mapped to the element of range. How can we name this relationship or this function? We usually use the lower letter F, G, H, something like that, which is the English letters. Or you can guess that in this course we will be using the Greek one, and delta is the one that we will be using a lot. All right. So far We have learned sigma in the Greek, alphabet. We learned lambda. We learned gamma, and we learned delta. What else we learn? Epsilon. Yeah, so these are the alphabet that we will be using. Let me take an example. Here is the same example I just took. Let's name it, for example, in this time, instead of G, we can call it, let's say, H, for example, right? The point is that when we define a function this way, we can show this function by algebraic notation. How? Look at this. Let me take the same example that I took in the previous slide. This is the same example. We can translate this relationship by an algebraic notation. How? So the function name is h. We would say h of John equal to what? Equal to a. H of Tom equal to C and so forth, right? H of Eve equal to F. So this is called algebraic notation of function, something like that. Okay, now let me give you some notes about this stuff I said. Let me ask the very important question. What is h of Ted here? Yeah. So when we don't have any value for this, we just say, okay, it is undefined. We cannot say anything about that, right? We should be silent about that. All right. This question and this answer shows that it is not the case that all of the elements of the domain should be defined. In some cases, it is not defined like this. And it is not the case that all of the elements of range should be assigned by something. In some cases like this, we don't have any assignment for this. All right. Okay. I am sure some of you guys that are calculus expert, you might say, hey, wait a minute, wait a minute. We have learned in the calculus that the domain, for example, of this, the domain of this, it should be all defined. Yeah? In calculus, we learned that the domain of this is R plus. It cannot be R minus. In the real numbers domain we are talking about, of course, in the imaginary domain, R minus, it can be all of R, right? But in this domain, you would say, okay, all of this should be meaningful. If you put a -1 here or -2 here, it is meaningless, right? Yeah, if you ask this question, you are right in the calculus. But in computer science, we don't care about this. Because just imagine this is a class, and this poor Ted missed one of these tests, right? Should we remove it from the class because he missed it? Yeah, in computer science is different, right? We would say h of Ted is undefined, and we are good for that. So we don't compare ourselves with the calculus. All right, let's see what we got. So this is one note. Another note I have, actually, I mentioned this in the previous slides, that is it possible for example, Mary has two grades at the same time? Yeah, you would say no, definitely no. It is meaningless, right? It is a contradiction, right? Another example for this, probably, if you are making a chart from the fever of a patient, right? You would have time here, for example, at 8 o'clock, the fever of the patient was, let's say, 97, and at the same time it was 100. It is impossible, right? Yeah, it is impossible. That's why we said, if there is a relationship, if there is a mapping between the elements of the domain and the elements of range, it should be unique. Yeah. Let me tell you a story about the calculus. You remember in calculus, uh, they told you that, for example, this is not a function. And m- most likely you ask why. They said, okay, when we have one x here and 2y, it is not a function. And if you kill yourself, okay, why? By definition, nobody, at least in my case, I asked many of the professors and my teachers in high school and in the university, but believe me, no one knew that. And this is a very simple example that it is impossible because we use mathematics to model the universe. And when in the universe such thing does not happening, right? That's why mathematicians define that this cannot be a function because at the same time, one x cannot have two values. Okay. Anyway, one more time. If there is a mapping, it should be unique. All right. Okay. Now we want to look at the function from different angle. The question is, we learned that this is an algebraic notation of this function. Can I use a set to define this? What does it mean? For example, if I say, okay, John is A, so there is a relationship between John and A. So I can represent this, this relationship with the order pair. And how about Tom and C? Yeah, the same thing. Tom and C, and so forth, right? Is this possible? Yeah, it is possible. So we can look at the functions from different angles and use the sets to represent a function and its rules, right? Yeah, this one. Okay, if this is the case, then if I ask you, what is so this is a set, right? This is a set. What is the universal set of this set? We call it H. What is the universal set of H? So just recall that universal set was a set that contains all possible values that we are talking about, right? How can I make the universal set of H? Yeah, it's Cartesian product between S and G. So I was saying that that universal set should contain all possible members like this. So if I create the Cartesian product between S and G, what I get? I get John and let's say just J, A, J and B, J and C, J and D, J and F, and then Tom. So you see, it has all possible values of this kind. All right. Okay, fantastic. Can I define now? This is a universal set. Can I say that any subset of this U can be a function? So not, no, I am not talking about this function, another function. For example, let me define H1 as For example, John B, and let's say Ted A. Is this a function? In Yeah, if we just imagine that it was a test, yeah, in that particular test, only John and Ted was present, right? The rest of them, maybe they went for demonstration, whatever, I don't know, the party. Yeah, it's not the case that all of them are a subset of this U can be a function. It's not the case because if we John, for example, A and John and B, this is a subset of the U, right? But it is not a function. So some of them we should be eliminate them. So if we have John, it should be unique. We have another very important concept here. We call it total function. Most likely you have not heard about that because this is just for this course. It is not defined in the calculus. So what is total function? It is a function whose domain elements, all of the domain elements are defined. Okay, let me take an example. So look at this domain, all of them are defined. We call this total function. You will see later that why it is important. And on the other hand, we have partial function. Partial function is a function who at least one of the domain elements is undefined. For example, this guy. So at least one is enough. So if you find one element that it is not defined or it is undefined, then you would say this function is partial. Okay? So at least one. Here we have one, two, three, but at least one is enough. Let me what I have for you as an exercise. In this exercise, I asked you definition of the function is this based on this Q and this sigma and this gamma. And I asked you to first of all find out what is the domain and what is the range. And then I asked you represent the universal set of this delta as a quadruple, is a set of quadruples. So you see one, this guy is 2, and this guy is 3, right? On the domain, you have a in 3 tuple, and range is the fourth one. So in this case, you can have a 3 tuple here and, for example, Q0 here. So, for example, Q0, let's say A, and then X, something like that, and you can define it with a quadruple, like this, right? In both cases, it is correct. But here, as I ask you to create this one. I have another exercise for you guys. This one probably very easy. I asked you to write the algebraic notation of this, this function. Yeah, in some cases like this, you can find a pattern, right? So f of 0, you would say 1. F of 1, you would say 2, and so forth, right? Algebraic notation never end here, right? And since there is a pattern here, you can say, okay, f of x equal to x plus 1. Yeah, you see? So this kind of function that we are very familiar in the calculus is very a small portion of functions that there is a pattern that we can, create an equation or function like this. But in general, it's not the case. Another exercise I have here, I ask you, so this is the rule. I ask you what is the domain, what is the range, and write the rule of delta by using algebraic notation, which is very easy. Just in exercise 4, I ask you to write a Java code that implement the function of exercise 2. And in exercise 5, I gave you a Java code and I ask you what is the range and what is the domain. Anyway, this is whatever I had for the function, that much that we need for this course. So in the graphs, which is very important, especially in this course, it is another mathematical construct or structure. And again, we are talking about the sets. So we have two sets. So one of them is a non-empty finite set that we call them vertices or also nodes and or states. In this course, actually, we call it states. But for these preliminary lectures, let's call them vertices. All right. So it's a non-empty and finite. So these both of them are important. And we have a finite set of the edges. So here it can be empty as well, right? And we know that each edge connect to vertices. For example, something like this, right? So we have two sets, and this E and index 1, 3, it means that the vertices 1 and 3 are connected. So if you draw the graph, you will have something like this, right? So we have three vertices and two edges, okay? So this graph is undirected. So there is no direction here, but in most cases, the direction is important, especially for us in this course. So directed graph is the direction of the edges matters here, right? So we show the edges with an ordered pair like this, a start vertex, end vertex. So this will be our pattern to represent each edge, all right? As I said, in this course, we always use the directed graph. Let me take some examples. We're gonna draw a diagram with the following specification. So this is the vertices and this is the edges. So if you draw that, you will get something like this. Okay, the things that are important for us is these terminologies and the concepts and their definition. So the first terminology is walk. Let's see what is the walk. So a sequence of edges, like this guy, is called walk. The only restriction it has is that the ending point of the edge of this edge should be the starting point of this, the next one. So this is the only restriction we have. So if we have such sequence of the edges, then we call it a walk. All right. Let me take an example. So let's see which one is walk. One edge, V1, V3. All right. We go from V1 to V3. So definitely this is a walk because it's just one edge. Another one, V1 to V3 and V3 to V3. This is another walk. The ending point is the starting point of the next one. How about this one? V1 to V3, V3 to V1, and V1 to V3. We just need to check that these two are equal, these two are equal, right? And we have not jumped from one, for example, if you jump from here to here, it's not a walk. You should walk on the edges to have a walk like this. All right. Okay. So what is the length of a walk? The length of a walk is the number of the edges that we traverse, right? Yeah, in the previous examples, the length of V1 to V3 is 1. So you just need to just count the number of edges. Here we have 2, and here we have 3. So you should be careful that first, you need to know that it is a walk, and then uh, try to count the number of edges. So what is path? A path is a walk. First of all, it should be a walk, but no edges are repeated. Or, in other words, every edge should be traversed or visited only once. All right? Let me take some examples. Which one is path? V1 to V3, it's just one edge. So no edges is repeated. It is a walk and it is a path. How about V1 to V3 and V3 to V3? V1 to V3 and V3 to V3. Again, this edge and this edge is traversed only once. So this is a path. How about this one? V1 to V3, V3 to V1, and V1 again to V3. So this guy is traversed twice. So this is not a path, but it is a walk, of course. How about simple path? Simple path is a path, first of all, but no vertices should be, repeated. Or in other words, every vertex should be visited only once. Let me take an example. Is this a simple path? Pay attention that it should be first a path, then we talk about whether it is a simple path or not. Okay, V1 to V3, V1 to V3, it's just one edge and no vertices is repeated, right? This was, visited only once, so this is a simple path, definitely. How about V1 to V3 and V3 to V3? And you see that this vertex is visited twice. So this is not a simple path. And the third one, V1 to V3, V3 to V1, and V1 to V3 again. So this is not a path. If it is not a path, definitely it is not a simple path too. So first we should prove that it is a path, then we talk about whether the vertices are repeated or not. So definitely it is not a simple path. How about loop? Loop is an edge from one vertex to itself. Yeah, like this. Okay. Is there any other loop here? No, that's the only one. How about cycle? Cycle is a walk from a vertex, so the starting point is called base, to itself. So we start from one vertex and we should go to some other places and return back to the same thing that we call it base. In that case, we call it uh, a cycle. But pay attention that it is a walk, first of all, and no repeated edges. So no edges should be repeated. So if you combine these two concepts, a walk that no repeated edges, it is equivalent a path, right? So instead of this, we could say it is a path that it goes from one vertex to itself, right? So yeah, let me take an example and then we return back to this, rewarding. of this definition. All right. So this is a cycle V1 to V3, V3 to V1. Up to this point, it is a cycle. But if we repeat, V1 again, V1 to V3, V3 to V1, it is not, it's not a cycle anymore because this guy and this guy is repeated. All right. So this is not a cycle. How about this one? V1 to V3 and V3 to V1. Yeah, as I said, it is a cycle because only this guy is repeated and it is, based on the definition. It is a valid cycle. How about this one? V1 to V3, V3 to V3, and V3 to V1, right? So this edge and this edge and this edge are visited only once, and we started from here and we return back to here. So all of these, requirements are satisfied. So this is a, cycle, definitely. All right. Now let's get back to our rewarding thing. So this walk and these no repeated edges, if we combine them, walk plus no repeated edges is equivalent to path. So we can reward this definition like this. A cycle is a path from a vertex called base to itself. All right. How about a simple cycle? When we add this simple, it means that no vertices should be repeated. Okay, so it should be a cycle, but no vertices except the base, of course, when we start from the base and we return back. So base is the only vertex that can be repeated twice, not more than twice. Pay attention, please. So not more than twice. So it is a cycle, first of all. No vertices other than base is repeated. Let me take an example. Which one is a simple cycle? So V1 to V3, V3 to V1, V1 to V3. So this is not a cycle. Definitely it is not a simple cycle. How about this one? V1 to V3 and V3 to V1. Yeah, it was a cycle. Now we know that based on this definition, it is a simple cycle. And how about this one? V1 to V3 and V3 to V3, V3 to V1. You see, this guy is repeated twice. It is a cycle, but it is not a simple cycle. So one point here I mentioned here, even the base should not be repeated more than twice. That's an important thing. So if we have, for example, it goes from here to here and here to here, and then if we have a loop here and we traverse this loop, then it is not a simple cycle, right? That's what we had for the terminology of the graph. The only thing remained here is another concept that we call it one-dimensional projection. We can apply this for any kind of walk. As we saw, walk is a very general concept. Yeah, it was a very wide concept that whatever we learned so far, all of them are walk, but you know, they have more restriction, more restriction, more restriction until we reach the simple cycle. That is the most restricted one. All right. Now the question is, what is one-dimensional projection of a walk. So let me explain that with this question. Look at this walk from V1 to V2. It goes here V1 to V3, V3 to V1, V1 to V3 again, and then V3 to V2. So this is a walk, definitely. But when we show this sequence of the edges like this, it looks like a twisted strain or whatever. For simplifying this and understanding what's going on, we can project this, walk in one dimension. In other words, we unwind this walk and put it in one dimension, and we call it one-dimensional projection. Okay, you see, V1 to V3, V1 to V3, V3 to V1, V3 to V1, and so forth until the end, right? At this point, I don't have any application for this. The only thing that I can say that sometimes it is easier when we show a walk like this. It is easier to understand and it is easier to study right now. But later we will see that how we can use this one-dimensional projection. The length of the this walk is the number of edges. So 1, 2, 3, and 4 here. Okay, that's what I had for today. See you guys in the next lecture.